This is Ideas Worth Exploring by Mark MacDonald. According to legend, in a region of ancient Greece called Magnesia, there lived a shepherd boy named Magnus. Magnus was tending his flock when one day he stepped on a peculiar piece of rock, and the nails of his shoes stuck to it. Magnus of Magnesia had discovered a piece of magnetite, which is a naturally occurring magnet. Magnets are basically magic. They pull on metal objects without even touching them. But like most forms of magic, magnets follow a strict set of rules that can be discovered through investigation. So let's investigate. This is the second part of a two-part series about electricity and magnetism. If you haven't listened to the first part, I highly recommend that you do. But now that you've ignored my advice, let's begin. Electricity and magnetism are actually two aspects of the same force if you believe in Einstein's special relativity. Einstein combined electricity and magnetism into a single thing called electromagnetism. But unless you just really love relativity, it usually makes more sense to consider them separately. Still, magnetism is definitely closely related to electricity. Last time, we talked about how static electricity is caused by electric charges that are static, or sitting still, and how moving charges are called an electric current. Static electricity should bring to mind a balloon sticking to the ceiling, and an electric current should bring to mind a light bulb or a toaster. Today, we're going to talk about how an electric current can be used to make an electromagnet, and how you can create an electromagnet using a battery and a piece of wire. And then, how an electromagnet is related to a permanent magnet like the kind stuck to your fridge. Fair warning, since you're probably already used to how a permanent magnet works, I'm going to use permanent magnets as examples before I explain why they work. If you don't like that, then I don't like you. Hans Christian Ørsted, a close friend of Hans Christian Andersen, discovered that when you place a compass near a wire with electric current flowing through it, the compass needle moves. Instead of pointing north, the compass points perpendicular to the wire. Later, a French physicist named Ampere discovered that two wires carrying electric current will exert a force on each other and will either push each other apart or attract each other, depending on which way the current is flowing. We now know that both of these phenomena can be explained like this. Moving electric charge creates a magnetic force. An electric force is produced by charged particles such as an electron. However, with the magnetic force, there's no particle, no magnetitron that produces it. No such thing. Instead, whenever charge is moving, for example, when there's a current in a wire, it produces a magnetic field. So, what's a magnetic field? It's where a farmer grows his magnets. Just kidding. A magnetic field is a different way of thinking about a magnetic force. Technically, I was wrong to say that a moving charge creates a magnetic force. That's because to have a magnetic force, you need to have a charge or another magnet to act on. But you could still calculate what the force would be on a hypothetical charge moving through any point in space, and we call that the magnetic field. A field is another way to think about forces without having to specify what the force is acting on, and it makes the math easier in some cases, and one of the rules of science is that if you can make the math easier, then you do it. Let's talk about electromagnets. We've established that a moving electric charge creates a magnetic field. Why? I can't answer that unless you want to delve deep into special relativity, so I guess either take my word for it or pause this episode and spend a few hours Googling special relativity. Welcome back to Ideas Worth Exploring. Now that you've convinced yourself that moving electric charge creates a magnetic field, we can talk about how an electromagnet works. A wire with a current flowing through it creates a magnetic field. If you wrap the wire in loops, then the magnetic field from each of the loops will add together. One loop, two loop, red loop, blue loop. The magnetic field from each of the loops adds together and you get a strong magnetic field overall. That's the basis for an electromagnet. The field around a single wire is weak, but the way the math works out is that the field around 100 loops of wire is about 100 times stronger than around a single loop. You could make an electromagnet at home with just a battery and a copper wire. But be careful not to shock yourself. Also, make sure to make your homemade magnet stronger, you can wrap the wire around an iron nail, for reasons that I'll get into later. A magnetic field is made whenever a charged particle moves. It doesn't matter how you move it. You can push it, you can spin it, you can swing it around your head. When you rub a balloon against your hair, the balloon becomes charged, which means if you move it around, it creates a magnetic field. because moving charge creates a magnetic field. Take a minute to think about that. Does that mean that a moving charged balloon will attract paper clips? Answer: the magnetic field it creates is too small for that, but it might stick to a paperclip because of electric forces, not magnetic. You get a much stronger and much more stable magnetic field by having a steady current through a wire. As long as the current is flowing, you have a magnetic field, and if you stop the current, the magnet turns off. That's what an electromagnet is. Keep that in mind for a minute while I change the subject. So, let's talk about compasses. Compasses point north, right? And it's because of magnetism, right? So what, is the Earth just a giant magnet? Are there like a bunch of magnetic rocks that just happen to be sitting on the North Pole? That would sure be convenient, but nope. There isn't a coincidentally large concentration of magnetic rocks at the North Pole. It's much stranger than that. The Earth is basically a giant electromagnet. Deep inside the Earth, there's a bunch of molten iron and nickel flowing around. These molten metals are charged, and by now I shouldn't even have to say it. When charges move, it creates a magnetic field. The specifics of the moving currents of metal and the math of how the whole thing works are still not well understood. Google magnetohydrodynamics or dynamo theory for more. Because of all the magnetohydrodynamic stuff, the Earth produces a magnetic field, and that's what moves the compass needle so it points north. So, moving charges in the Earth's outer core make a magnetic field around the entire Earth, and the Earth's magnetic field is oriented in a way that makes a compass point north. The fact that it points north is not a total coincidence. The Earth's axis of rotation is directly related to the direction of the magnetic field, but that's some more magnetohydrodynamics, and sadly this isn't an episode about magnetohydrodynamics, but I do enjoy saying the word magnetohydrodynamics. Do compasses in the southern hemisphere point south? What's your hypothesis? And the answer in 3, 2, 1, it turns out that all compasses point both north and south. You might be thinking, yes, a compass points north, and if you know which way north is, you can just reverse it and that's south. But that's not quite right. A magnetic compass, like all magnets, is bipolar. Sorry, I actually meant dipolar. I mixed up my Latin and Greek roots. A magnet is dipolar. Contrast it with an electric charge that is monopolar. It's either positive or negative. A magnet also has two different ways to be, which we call the magnet's north pole and south pole, and every magnet has both of them. On a compass, the compass magnet's north pole points north, and the compass's south pole points south. That's why a bar magnet sometimes has a little N and an S on it. The magnet lines up with the Earth's magnetic field, with the N pointing north and the S pointing south. You always have both poles, so even in the southern hemisphere, the red needle on your compass will point north and the other needle will point south. So think of the little bar magnet with the N and the S on it. What happens if you break it in half? You'll have one half that's north and one half that's south, right? Wrong. On the half that has the N on it, you can go ahead and take a Sharpie and write a little S on the broken end, because the broken end just became a new south pole. Magnets must be dipoles. If you get rid of the S side, it'll grow a new one. But it's not quite as magic as I just made it sound. You can think of a bar magnet as a bunch of little magnets glued together, and each of the little magnets has a north and a south pole. Cutting it in half just exposes the south pole of a different one of the little magnets. Also, just like with electricity, opposites attract. A magnet's north pole will attract the south pole of another magnet. A magnet's north pole will be repelled from the north pole of another magnet. That's a fact that we've observed for hundreds of years. What does this mean for a little magnetic compass? If the north pole of your compass points north, then that means the Earth's magnetic field has a magnetic south pole to the north of you. Earth's magnetic poles are the exact opposite of what you'd think. The magnetic south pole is up near where Santa lives, and the magnetic north pole is with the penguins in Antarctica. Kinda weird. So, the Earth is an electromagnet created by moving charges in the liquid metal of Earth's core. Capiche? Now we can talk about permanent magnets, and I'm happy to tell you that it gets even weirder. Okay, permanent magnets. First thing to know, a spinning electric charge causes a magnetic field, just like a moving one does. Second, because of a weird quantum thing, Electrons have a property called quotation marks spin, which is a terrible name because they're not actually spinning, but it's also helpful in this one exact situation we're talking about right now, because quotation marks spin causes a magnetic field in exactly the same way that a spinning charge does. It would be more helpful if instead of spin, we said that electrons have a property called tiny magnet, but once a name sticks, it's freakishly hard to change it, so we're stuck with spin. So, because of electron spin, every electron creates a magnetic field. In natural materials, electrons are usually found in even numbers. Go back to the episode on the periodic table if you want to know why. The spin can be in two different directions, up or down, just like a bar magnet with the end facing up or with the end facing down. Because of more quantum shenanigans, a spin up electron always pairs with a spin down electron, and when this happens, then the two magnetic fields cancel each other out. That's why your socks aren't magnetic. But some materials, like iron, have electrons that are not paired up. In these materials, quantum shenanigans cause a bunch of electron spins to line up in the same direction. This creates a magnetic field large enough to stick a preschooler's drawing to the refrigerator. So, because quantum, a bunch of the tiny magnets and electrons all lined up, and that made the lump of iron into a permanent magnet, the kind that our shepherd friend Magnus found. But sometimes a non-magnet can be magnetized. How does that work? The non-magnetized iron is made of groups of atoms called domains that behave like I just described, as mini-magnets. But these domains are arranged randomly and cancel each other out, like a bunch of people pushing from different directions. When you put the paperclip next to a permanent magnet, the domains in the paperclip shift, so they point in the same direction. When this happens, the paperclip becomes magnetized and can stick to other paperclips because its domains are all aligned. But if you drop the paperclip or bang it against the table, the domains will move around and the paperclip will become demagnetized. That's why if you have a good permanent magnet, you need to be careful not to drop it or bang it against things, because every time you do, it weakens the magnet a little. Why do magnets only attract some metals and not others? Because some metals are made of socks. And what I mean by that is only some metals, like iron, nickel, and cobalt, have an unpaired electron, and the rest of the metals have paired electrons, like your socks do. The only metals that are strongly attracted to a magnet are the metals that have the potential to become magnets themselves. I'm sure there's some deep life lesson you can draw from that. In summary, a permanent magnet is the result of quantum effects, but in the end, it's the same thing as an electromagnet, just instead of a magnetic field made by moving charges, it's made by electron spin. What attracts the knight in shining armor even more than the damsel in distress? Magnets! And now you know why. Electromagnets work because moving charge makes a magnetic field. The Earth is a giant electromagnet, and a compass needle is a permanent magnet. Permanent magnets work because quantum. Inside a permanent magnet are domains that are each a mini magnet. If the domains are arranged randomly, no magnet. But if they line up, magnet. That's why you should put an iron nail inside your coil of wire if you're trying to make a homemade electromagnet, because the wire will make a small magnetic field that will make the domains in the nail line up, and then the nail will become a much stronger magnet than you can get with just the wire. Try it out. It's better than watching YouTube all day. And come back next time to talk about why Pluto is not a planet. Peace. This has been Ideas Worth Exploring by Mark McDonald.